All right, if you're following along in the text, we're on page 144, derivatives of trigonometric functions. So in this section, we're going to expound on the idea of the derivative as far as the formulas go and how to apply those formulas for the derivative. This means the general power rule, the sum rule, the difference rule, the product rule, quotient rules. These all still apply to the derivatives of trigonometric functions. The first trigonometric function that we need to know, the derivative of is sine x, or ddx of sine x, a derivative with respect to x of sine x, is cosine x. So in example one, we're asked to differentiate the function y. Given that y is equal to x squared times sine x. So the way that I want you to approach this problem is to one, recognize that the given function, x squared sine x, is a product of two differentiable functions. The first differentiable function being x squared, the second differentiable function being sine x. So because we're multiplying two differentiable functions, this is a product rule problem. Remember product rule, f prime g plus f g prime, the way that I have it in my notes. In this case, we're going to need f, g, f prime, and g prime, respectively. So here f, my first differentiable function, would be x squared. G, my second differentiable function, would be sine x. We need f prime and g prime. So given that f is x squared, f prime, or the derivative of x squared with respect to x, we can apply the general power rule, and that will give me 2x, taking our exponent, bringing it out front, multiplying by our exponent, and then decreasing by 1. And we can use our first derivative of trigonometric functions formula, keeping in mind that the derivative of sine x with respect to x is cosine x. Right. So now we have f, g, f prime, and g prime. So we can start working on the derivative, y prime, applying our product rule, f prime g plus f g prime. So f prime g, f prime, 2x, times g sine x, plus f g prime, f x squared, times g prime, which is cosine x. And so we just look to see if we can, well, first we multiply, get our products, and then see if we can combine like terms. 2x times sine x will just give me 2x sine x, plus x squared times cosine x will just give me x squared cosine x. This is actually the simplest way that we can write this. These are not like terms. So y prime, or if we differentiate y, which is x squared times sine x, y prime would be 2x sine x plus x squared cosine x. Had it been presented in another way, for example, x squared cosine x plus 2x sine x, it's exactly the same thing. All right. Remember that the way that the book presents the product rule is a different order, so we may very well see the order in which we can multiply and add presented differently. But keep in mind the commutative and associative properties for multiplication. The order in which we multiply and the order in which we add makes no difference. All right. Any questions on example one? All right. So we're going to need to know the derivatives of all 6 trigonometric functions. This is probably a good idea to bring this with you on the test day, where we can have this on the formula sheet. We cannot have work problems, but we can have, honestly, straightforward, we can just have the derivatives of trigonometric functions. So have this with you on the test. Very good idea. All right, so our first one, the derivative with respect to x of sine x, we already went over, is cosine x. Bless you. Our second, the derivative with respect to x of cosine x is negative sine x. The derivative with respect to x of tangent x is secant squared of x. The derivative with respect to x of cosecant x is negative cosecant x cotangent x. The derivative with respect to x of secant x is secant x tangent x. And the derivative with respect to x of cotangent x is negative cosecant squared of x. Once again, you can have this with you on the test. A good idea to bring this with you on the test. Example 2. Here, we're asked to differentiate f of x, which is secant x divided by 1 plus tangent x. So remember, like I've said before, any differentiation rule, one in of itself, not that difficult. What becomes the issue is knowing when to use what rule. So here, probably a good idea to know right off the bat that we're going to need the quotient rule to differentiate this function because we have two differentiable functions being divided. Those two differentiable functions, my numerator and my denominator, happen to be trigonometric. All right, so this is a quotient rule problem. We can use our formula, our formula sheet for the derivatives of trigonometric functions. So starting with f of x, which is secant x divided by 1 plus tangent x. This is a quotient rule problem. The quotient rule f prime g minus f g prime, all divided by g squared. So in this problem, my first differentiable function, f, will be secant x. My second differentiable function, g, will be 1 plus tangent x. Still need f prime and g prime respectively. So given that f is secant x, f prime will be the derivative of secant x. We can look at our chart and see the derivative of secant x is secant x tangent x. And we still need g prime, given that g is 1 plus tangent x, g prime will be the derivative of 1, 0, no need for us to write it. And derivative of tangent x, we can get off our chart as well. And derivative of tangent x is secant squared of x. So now we have everything we need to start working on derivative. F prime of x, we just need to plug everything into its appropriate place in the quotient rule. Quotient rule f prime g, f prime, secant x tangent x. Times g, 1 plus tangent x. Minus f, secant x. Times g prime, secant squared of x. All of this is being divided by g squared. This problem that would be 1 plus tangent x raised to the second power. All right, so a common mistake when dealing with these trigonometric functions is that when people see two or more trigonometric functions, they start counting the functions they see as if they were terms. So here, secant x tangent x, bless you. A lot of people make the mistake of trying to FOIL out secant x tangent x times 1 plus tangent x, as if it was a binomial times a binomial. Remember, secant x tangent x is one value. There is no plus or minus sign in between those two, and multiplication is still a part of the same term. So we can't FOIL this, we have to distribute it. Bless you. At the end of the day, secant x tangent x is just one term, so it must be distributed. Secant x tangent x times 1 will give me secant x tangent x. Secant x tangent x times tangent x will give me secant x tangent squared of x. We're still subtracting the product of secant x times secant squared of x, which will give me secant cubed of x. All this is still being divided by 1 plus tangent x quantity squared. All right, so in my numerator, we have 3 terms. First term, secant x tangent x. Second term, secant x tangent squared of x. Third term, secant the cubed of x. All three of these terms have at least one secant x in common, so we can factor out a secant x from all three terms, which is going to leave me with tangent x plus tangent squared of x minus secant squared of x. All of this still being divided by 1 plus tangent x squared. Plus. This is when we want to remember that we have a Pythagorean identity dealing with tangent squared of x and secant squared of x. That identity is tangent squared of x minus secant squared of x is equal to -1. We can take this fact and make our substitution where we see tangent squared of x minus secant squared of x. Or this tangent squared of x minus secant squared of x is going to become -1. So now we have secant x times tangent x minus 1 divided by 1 plus tangent squared of x, tangent of x squared. And this is f prime of x, written in the simplest forms. Any questions on example 2? All right, example 3. Example 3 is on page 148. We're looking at figure 5 in the left-hand margin of page 148. Example 3 reads, an object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and is released at time t equals 0. It says see figure 5 and note that the downward direction is positive. Its position at time t is given by the function s. The position function, which is a function of time, f of t, is equal to 4 cosine t. We're asked to find the velocity and acceleration at time t and then use them to analyze the motion of the object. We're not going to focus on the analyzing of the motion of the object part. On the test, I would really focus on the velocity, acceleration, and how it relates to the position function, how the derivative is a relation, as well as focusing on the derivative of the trigonometric function cosine t. All right, so we're given the position function f of t, which is 4 times cosine t. And we want to remember that derivative of the position function gives me the velocity function. And to keep us honest, I'm going to use the Lebanese notation here. So the velocity function v, which is the derivative of the position function in terms of time, or the derivative of s with relation to time, or this would be d dt of the position function 4 times cosine t. So we're going to take the derivative of the position function 4 cosine t. We can use our constant multiple rule to see that this is really 4 times d dt of cosine t. Or we can pull out our scalar multiplier 4 and multiply that by the derivative of cosine t. We know the derivative of cosine is negative sine. So our answer would be -4 sine t. So the velocity function with relation to time, or v of t, -4 sine t. We're also asked to find the acceleration in relation to time. Remember, the acceleration function will be the derivative of the velocity function with relation to time, or dv dt. Or in this case, that would be ddt of our previous function, -4 sine t. We use our scalar multiplier rule, pulling out that -4. That's times the derivative with respect to time of sine t. And we know the derivative of sine is cosine. So this would be -4 cosine t. So the acceleration function with relation to time will be -4 cosine t. Any questions on example 3? Example 4. Example 4 states to find this 27th derivative of cosine x. Now, there is no rule saying that we can't just simply take the derivative 27 times and hope that we didn't make a human error in those 27 steps. Obviously, we want to find a more concise way of getting that answer and a more reliable answer, or a more reliable way to get that answer, because there's nothing stopping me from asking what's the 1037th derivative of cosine x. All right? So what we want to do is see if we can find any relation between the derivatives themselves. So we're trying to find the 27th derivative of cosine x. We want to first start with the function cosine x itself. So the first derivative of cosine, or f prime of x, derivative of cosine, negative sine. The second derivative, or the derivative of the derivative of negative sine. The derivative of sine is cosine. So if we ignore that scalar multiplier -1 for a second, that would give me a -1 times cosine x, or the derivative of negative sine would be negative cosine. The third derivative, or derivative of negative cosine, we know the derivative of cosine is negative sine. So we'll have a -1 times negative sine, which will give me a positive sine x. And the fourth derivative, or derivative of sine, we know the derivative of sine is cosine x. Fifth derivative of cosine, we can relate back. Derivative of cosine was negative sine. And it goes on in that same cycle. So we can see that this is a cycle of length 4, which means that any derivative that is divisible by 4, we know is just going to be cosine x. And if it's not divisible by 4, that means it has a remainder of 1, 2, or 3. So if it has a remainder of 1, it's negative sine x. Remainder of 2 is negative cosine x. Remainder of 3 is sine x. Can't have a remainder of 4 because that means it's divisible by 4. And if it's divisible by 4, our answer is cosine x. So for our original problem, the 27th derivative of cosine x we can start by noting that the 24th derivative of cosine x will be cosine x itself, because 24 is divisible by 4. So if this is the 24th derivative, 25th, 26th, 27th will be right here. Or the 27th derivative of cosine x will be equal to negative sine x. This is because 27 divided by 4 leaves me with a remainder of 3. Like I said, anything with a remainder of 3. Negative sine x. Oh, excuse me. That is positive sine x. Like I said, remainder of 3 would be sine x. So that's our final answer. Appreciate it all. Questions on example 4? Homework for this section, if you're in the 8th edition, starts on page 150. I want you to go over problems 5, 7, 9, 15, 17, 19, 21, and 39. We're actually going to start the chain rule on Monday. We're going to take 2 days for the chain rule. That's typically the section that gives a little bit of trouble. So we're going to take Monday and Wednesday to go over the chain rule. First, I'm going to introduce it to you on Monday. Then we're going to have an activity on Wednesday and have some more practice with it. That section is typically difficult, not because the chain rule itself is more hard than any other rule we've done, but to apply the chain rule, we must still remember the sum rule, the difference rule, the product rule, the quotient rule, constant multiple rule, the derivative of our trigonometric functions, and all of that on top of the rule that we're going to learn on Monday, which is the chain rule. So like I've said before, any rule one and of itself, not that difficult. What becomes difficult is knowing when to use what rule. And hint is the name. All right, product rule, quotient rule, when we have two differentiable functions that's being multiplied for product, being divided for quotient, sum, and difference is pretty straightforward. Typically, people don't have any issue with that. All right. If you have any questions, feel free to email. Remember, I'm available through Zoom, and good luck studying.